Hello everyone. So, I've gotten several requests for a partial fraction decomposition video, so I'm going to go ahead and make one for you guys. So we now know several techniques that we can use to evaluate integrals, one of which being partial fraction decomposition. So when I'm looking at this integral, I see that there's a lot of algebra going on. We have a quadratic in the numerator. We've got two binomials in the denominator, one of which being a quadratic. So I'm thinking, okay, we're gonna be needing to use one of the algebraic techniques that we have to evaluate integrals. And now what I'm going to look at is I'm going to ask myself, is this a proper fraction or an improper fraction? And this is a proper fraction. There's more x variables in the denominator than there are in the numerator. So that tells us that that is a proper fraction, and we can use partial fraction decomposition. So the way that we do that is we take all of what's inside of the integral and we set it equal to what we're going to make a partial fraction. So I go left to right, and I see that we run into our quadratic binomial here first. And anytime we see a quadratic, we write ax plus b, or whichever unknown we're on. Here we just started, so we're going to be on ax plus b. We could be on cx plus d. It doesn't matter as long if there's a quadratic. You have to have one of the unknown coefficients with an x and then one by itself. And then you just put that over that quadratic. All right, perfect. Next, we'll look at the next term. So we see that it's an x minus 7. And that's a linear term, so we'll just go at c. We don't need an x or anything else. We just need an unknown coefficient c if it's linear. And that's it split into a partial fraction. So we've split what's inside there, and we've made it into a partial fraction. So now what I would do is if this was a test, I'd go ahead and evaluate these integrals. So we have the integral of ax plus b over x squared plus 5 dx. That's going to be plus our second integral, which will be c over x minus 7 dx. And then to evaluate these, I'm going to go ahead and split that first integral into two integrals. So we'll have 3 total. And I'll say a times x over x squared plus 5 dx plus b times the integral 1 over x squared plus 5 dx and plus c times the integral 1 over x minus 7 dx. All right, perfect. And now we can go ahead and evaluate these 3 integrals using basic techniques. The first one, we'll use a U-substitution. We'll say u equals x squared plus 5. Then du equals 2x dx. And we'll have 1/2 du equals x dx. So to rewrite the integral in terms of u, we'll have a over 2 integral and then 1 over u du, which will equal a over 2 ln absolute value of u plus c, but we have 2 other integrals we need to solve, so I'll just leave the plus there. And then a over 2 ln absolute value x squared plus 5. 5 plus, and that'll be how we evaluate that first integral. Now this second integral will be, you can either use the trig subtables in your common integral table in your textbook, or we can go ahead and use trig substitution and evaluate this by hand. And I'm going to do that for you guys. I'm going to evaluate this by hand just to get a refresher on trig substitution. So we see x squared plus 5, so that means we're going to be using a trig substitution involving tangent. So we say x equals the square root of 5 tangent theta. That means that dx equals square root of 5 secant squared theta, d theta. And x squared plus 5 equals square root of 5 tangent theta squared plus 5. Just subbing what we said was equal to x in there. 5 tangent squared theta plus 5. Factor the 5 out, you get tangent squared theta plus 1 equals 5 secant squared theta. Perfect. And now we can go ahead and substitute all of that trig in there to hopefully make this integral easier. So we said dx is equal to the square root of 5 secant squared theta d theta. And we said x squared plus 5 is equal to 5 secant squared theta. So 5 secant squared theta. Perfect. Now we can evaluate this integral. So we'll have, we take out our constants there, b square root of 5 over 5. These go away, so we'll just be left with 1. So we'll be just left with the integral of d theta. B square root of 5 over 5. Integral d theta is just theta. Plus, and we still have one more integral to evaluate, so I'm just going to leave that plus there. Now we back sub, so we have b square root of 5 over 5. And theta we can solve up here. Okay, so that would equal theta equals tangent inverse x over 5, root of 5. Tangent inverse x over root 5. And we can simplify this even more if we wanted to. We can split that into b root 5 just to get rid of that square root in the numerator. Could write that as that. So it would just be left with b over square root 5. Tangent inverse of 1, x over root 5, and then plus our final integral. And I'm going to go ahead and move this guy down there. We have it all together. There we go. I'll draw an arrow pointing down. Perfect. Alrighty. Let's evaluate this last integral we have here. And this is how we would maximize our points on the test. So that way all we have left to do is find the coefficients a, b, and c. And let me draw an arrow pointing. There we go. Okay. Do I want to do that? Actually, I'll just leave that a big space. Perfect. All right. And this last one, you can just use a basic U substitution. So we say U equals x minus 7, du equals dx. So in terms of U, this would be integral of 1 over U, du, C ln absolute value of U plus K. And C ln absolute value, we said U is equal to x minus 7. plus k. Perfect. So now we have evaluated this integral. We just need to find the coefficients. We just need to find the values for the coefficients. Move that down there. Perfect. Okay. Draw an arrow. There we go. Perfect. So now we've done most of the work. I'd say we've done probably 80% of the work. So we've evaluated this integral. We just need to find what the values of a, b, and c are. And the way that we can do this is we can use the matrix and evaluate a matrix to find the values for a, b, and c. And that's the way that I do it. It works every single time. So we're going to go ahead and do that. So what we do is we'll set our original numerator. Ax plus b times, and we're going to write this, we're going to get rid of the fractions. So we're just going to write it all just as just terms. So we won't have any fractions. And the way that we get rid of the fractions is that we multiply the original denominator by each one of these numerators. And then cross the like terms out because they'll equal 1. So this will go away with that, and we'll just be left with x minus 7 in the numerator there. X minus 7 plus. Same thing with c. We'll just be left with x squared plus 5. And that gets rid of the fractions for us. It's a little easier to compute and look at. So now we'll just do our simplifications. We'll FOIL. We'll have ax squared plus, actually it'd be minus 7 ax plus bx minus 7b. And we'll just distribute that cx squared plus 5c. Perfect. And now we want to combine our like terms. So x squared goes with that guy. This goes with this guy. And our constants. All right, perfect. We'll write it in standard form, so we'll put our x squareds first. Let's see, what else do we have? Cx squared plus squared minus 7ax and plus bx minus 7b plus 5c. Perfect. And now what we want to do is we want to factor out the variables. So we want to factor out any x squareds or any x's, and we just want to leave our unknown coefficients inside parentheses. So we'll do just that. We'll factor out the x squareds from these guys. We'll be left with a plus c. So we'll factor out a x. Be left with negative 7a plus b. And the last one's the constants. We don't need to factor out any x's, so we'll just leave them without parentheses. And I'll rewrite what it's all equal to. All right, perfect. So now we're ready to go ahead and insert this into a matrix or create a matrix. And I always write the general case, just it reminds me where everything needs to go. We'll have a 3x4 matrix. Perfect. So now, the way that I create my matrix or generate it is I look for, all right, so this row here is going to have all of our x squareds in it. So look at my x squared. So we have a plus c. So I go to make it. So we have 1a, 1. And we have 0 b's, so 0. And we have 1c, so we'll go 1. And then that has to equal 5x squareds over there. So 5. Now we'll look at our x terms. Same thing. We'll look at what's inside the parentheses. We see we have negative 7a's, we have 1b, and we have 0c's. Then we look over at our other side, and it needs to equal 1. All right, perfect. Lastly, we look at our constants here. So we have 0a's, negative 7b's, and 5c's. And that has to equal 18. All right, perfect. Draw our line here to separate what all of those have to equal. And now we're ready to go ahead and insert this into our TI-84. So let me show you how we do that. So once you get your TI-84 open, you want to go to Second. You want to go to Matrix. Scroll over to Edit, and I'll go ahead and edit it in, let's see, go ahead and edit it in E. All right, and once you get here, you want to type in what type of matrix we have. So we have a 3 by 4. Let me get this so I can see it. There we go. All right, perfect. And then we go ahead and type what we see. So we have 1, we have a 0, we have a 1, and we have a 5. Here we have a negative 7, a 1, a 0, a 1, and last row we have a 0, and a negative 7, a 5, and 18. Perfect. And now I always double check to make sure I typed it in right. So we have a 1, 0, 1, 5, negative 7, 1, 0, 1, 0, negative 7, 5, 18. Perfect. So now we can go ahead and hit Second, Quit, and then go back into our matrix. So we go Second, and then we hit X inverse. We go to Math. We're going to go to the capital letter B, RREF. Second matrix again. Go to Names. And then go to wherever you typed it in. I typed it in E. So I'll go to E. Hit Enter again. And you'll see your solution set for your matrix. We'll go ahead and write that. Go there. RREF. Reduced row echelon form. 0, 0, 1, 0, and 0, 0, 1. So that just means it's a consistent matrix. And what do we have? 0, 1, and 5. 0, 1, 5. Perfect. And this first one will be equal to A. The second one will be equal to B. Third one will be equal to C. All right. So now that we have our coefficients, we have values for our coefficients, we can just go ahead and replace our A, B, and C placeholders with their respective values. So we said A is equal to 0. Said B was equal to 1. And C is equal to 5. Okay, perfect. And that first one will just equal 0, so be just left with 1 over root 5 tangent inverse x over root 5 plus 5 ln absolute value x minus 7 plus a k. And that is our final solution. So that's how we do partial fraction decomposition. Again, if you guys do have any other questions, any questions at all, feel free to ask me, feel free to contact me, send me a group me, send me an email and say, hey, Josh, I'm stuck on this problem. Can you help me out? And I'll say, of course I can. Again, feel free to ask me any questions, and I'm always happy to help you guys out. I hope you guys have a great day, and I'll see you guys whenever I see you. Have a good day, everyone.